This is the second in a series of videos introducing logic gates. It covers creating truth tables for combinations of simple logic gates. Combinations of logic gates manipulate pulses of electricity, and because these pulses represent binary ones and zeros, combinations of logic gates can perform useful data operations, such as comparing values, performing arithmetic, and even storing data. Being able to create truth tables for combinations of logic gates is an extremely important aspect of computer circuit design, because truth tables can help us to see how circuits work. Let's begin by reviewing the building blocks. This is a NOT gate. The input has been labelled A and the output has been labelled Z. You can see in the truth table that when A is 0, Z is 1, and when A is 1, Z is 0. This is an AND gate. There are two inputs here. When both inputs are 1, the output at Z is a 1. In all other circumstances, the output is 0. By convention, the combinations of inputs count upwards in base 10. This helps to ensure that they're all covered. And finally, this is the OR gate. When one or the other input is a 1, the output is a 1. Also, when both inputs are 1, the output is a 1. Here's a combination of gates. The overall combination has two inputs and one output, but there are two gates involved. To come up with a truth table for this combination of gates, it's useful to consider point C. Each value of C is the result of passing A and B through an OR gate. You can see when one or the other of A and B, or both, are a 1, the value at C is a 1. Then, to get the value of Z, we pass each value of C through a NOT gate. You can see that each value of Z is simply the inverse of C. So here's our overall truth table. And we can discard column C if we're not interested in those values. This combination of gates is sometimes referred to as the NOT-OR combination, or NOR for short. It's actually very useful, as you'll see in a later video. This combination is an AND gate followed by a NOT gate. To get the values at Z, we can consider position C first of all. Each value at C is simply the result of passing combinations of A and B through an AND gate. You can see in the bottom row, when both A and B are 1, the value of C is 1. To get each value of Z, we then pass each value of C through a NOT gate. So here's our truth table. We can ignore values of C if we're not interested. This combination of gates is also extremely useful, and it's sometimes referred to as the NOT-AND combination, or simply NAND for short. Here's an example involving 3 logic gates. Values of A and B are being passed through NOT gates before being combined through an OR gate. To produce a truth table for this combination, it's useful to consider points C and D. Each value of C is simply the inverse of each value of A. Each value of D is simply the inverse of each value of B. And now that we have values for C and D, we can combine them through an OR gate to give us each value of Z. Here's our truth table. You can ignore C and D now. You might have noticed that this truth table is exactly the same truth table for the NOT-AND combination that we saw earlier. It's not uncommon for different combinations of gates to produce the same output. Here's another example. Perhaps you'd like to give this one a go yourself. Pause the video now if you'd like to try it, and resume in a few minutes and I'll show you the solution. So, just like we did before, it's useful to consider points C and D. Each value of C is the result of passing each value of A through a NOT gate. Each value of D is the result of passing each value of B through a NOT gate. And now that we have values of C and D, we can pass combinations of these through an AND gate, giving us each value of Z. Here's our truth table. Did you get the same? You might have noticed that this is the same truth table as the NOT OR combination that you saw earlier on. In this example, we have 3 inputs, A, B and C, and only 1 output. That means our truth table has 8 rows in it. Each combination of A, B and C should count upwards in base 10 to ensure that you've got them all covered. To solve this one, we need to consider intermediate point D. Each value of D can be arrived at by passing pairs of values for B and C through an OR gate. We then take each value of A along with each value of D and pass them through an AND gate. Here's the result. Here's another example. Perhaps you'd like to give this one a go yourself. Pause the video now if you want to give it a try, and I'll show you the solution in a few moments when you resume. To solve this one, we'll consider intermediate point D. Each value of D comes from passing pairs of values for B and C through an AND gate. And then each value of Z comes from passing pairs of values of D and A through an OR gate. Did you get this result? In this example, we have 3 inputs, as we did before, but notice that input A has been split. Input A is feeding the top and the bottom AND gate. In this example, you're also being asked to include intermediate points D and E in the truth table. Otherwise, there's nothing terribly new here. To get each value of D, we pass combinations of A and B through an AND gate. Then, to get each value of E, we pass combinations of A and C through an AND gate. Now that we have pairs of values for D and E, we can pass them through an OR gate to give us values of Z. Here's a similar example. If you'd like to give this a go, pause the video now, and I'll show you the solution in a moment. You're being asked to create the truth table from scratch this time. OK, before tackling this one, notice that input B has been split. Input B is feeding the top AND gate and the NOT gate. Because we've only got 2 inputs, we're only going to need 4 rows in the truth table. First, work out values of C. Each value of C can be arrived at by passing combinations of A and B through an AND gate. Then work out values of D. Each value of D is simply the inverse of each value of B. And finally, to get each value of Z, we pass combinations of C and D through the second AND gate. Here's our truth table. In this example, we have 4 inputs. That means we're going to need 2 to the power 4, that's 16 combinations of inputs, and therefore 16 rows in the truth table. Perhaps you'd like to give this one a go yourself. I'll show you the solution in a moment. And here's the solution. Notice how we're counting from 0 to 15 as we read down the combinations of input values. Each value of E is A and B. Each value of F is C and D. And each value of Z is E or F. If you've done yours as I suggested, you should have exactly the same truth table. This final example looks a little bit more complicated than anything you've seen before, but there's nothing new here. Work through it systematically and you'll come up with a result. Why not give it a try yourself? OK, before tackling this one, notice that input A has been split. It's feeding the top NOT gate and the bottom AND gate. Notice also that input B has been split. B is feeding the bottom NOT gate and the top AND gate. To produce a truth table, we should consider intermediate points C, D, E and F. So we're going to need a truth table with 4 rows and 7 columns. Starting with C. C is simply not A. Then D is simply not B. Now that we have C and D, we can consider E. E is B and C. F is A and D. And finally, Z is E or F. Here's our truth table. This is actually a very useful combination of logic gates. It's sometimes referred to as the exclusive OR the XOR for short. If you examine the truth table, you can see that it's almost the same as an OR gate. When one or the other input is a 1, the output is a 1. When both inputs are 1, the output is a 0. So quite literally, if one or the other input is a 1, the output will be a 1, exclusively. This combination of gates even has its own symbol.